generation of the random numbers we were discussing about. I said like there are different methods. In that, the very first method is the linear congruential method, which we are going to learn. Already we know about the different methods. That is a linear congruential method and a multiple. When we take it, that is, in the previous class we discussed about a combined linear congruential generators and random number streams. So here the very first thing is the generation of it by using the LCM method or linear congruential method. So here when you are taking it, it is how are you going to produce a sequence of integers. So when you are taking it, that is, if we want to produce a sequence of numbers, that is x1, x2, x3 and so on, okay, which are between the range when we take it, that is 0 to 1 as usual. But let us consider that it is given as the sequence numbers, it is 0 to m minus 1, 0 to m is the range what we are taking it. So this is represented as xi plus 1. Okay, when I want to take xi plus 1, the random number I plus 1, when I want to generate it, it's given as axi plus c mod m. What is this a? A is a multiplier array. We can say that it's a constant multiplier, and the c is the increment what I give it. Okay, the coefficient of x. Here the x is the increment and the mod m is the modulus what we are taking within the range 0 to m. When I said that it is up to m, what am I taking it? So the random numbers I can generate for I, that is xi is the given expression. The I can be from 0 to m. So I can take 0, 1, 2 and so on. So the selection of values when we are taking it, what should be a, c and m? Because a, as I said, it is a constant multiplier, it's used for all the things. Similarly, c is the increment what we are taking from, and m is a modulus. So how are we going to select these values? To select these values, the very first thing is we are going to take a random number x naught. When I am taking x naught, when I is equal to 0, I don't have, that is, I is 0 when I take it. Directly, I can generate from x1 only. That is, I is 0 when I substitute, that is x1 I can take. But what is this x naught? X naught is also the first random number which we can say that it is also being selected. So here when we are going to select these values a, c, m and x naught, which is going to affect the statistical properties which we have discussed in our random numbers. So here these are going to affect the statistical properties of the cycle length. So here the random numbers which we are going to select it, they should not affect the properties of randomness, that is uniformity and independence. The next thing is that we have to take care the random integers which are being generated, that is from the range 0 to m minus 1 and to the, here the range what I am taking, it is from 0 to m minus 1, and here we are going to convert this random numbers to the integers. That is what we do take it, Ri is equal to xi by m. As you know, m is a modulus. So here we are going to convert this integers whatever we have generated as xi to the random numbers Ri. So Ri is given as xi by m 0, where I can range from 1 to, because x0 is already been given. So xi I is from 1, 2, 3, 4, 5 and so on we can take into. Let's take that example. The example. Okay. So here let us consider that the random number generation. It's been asked to generate a sequence of random numbers given x naught is 27, a is 17 and c is 43 and m is 100. So here the modulus we are going to generate the random numbers between 0 to 99. M minus 1 means up to 99 we are going to generate these values, and x naught when it is been given, now we start I from 1 only. The thing is that x1, so here when you take x1, as we have already seen that the x1 when you want to calculate it, the x1 is xi plus 1, that is 0 plus 1 is x1. It is given as a x naught, the expression what we have discussed in the previous slide, that is a x naught plus c into mod m what we had taken it. So a is given as 17 and x naught is given as 27 plus c is 43, which is a constant increment which I had taken for the very first number. The thing is 43 mod m, that is 100. I get it as 502 mod 100 is 2. So the first random number, the R1 is 2 by 100. I get it as 0.02 is the one what I get it, because the xi is generated, random number Ri is xi by m. M is, that is 2 by 100. Now when I want to generate this x2, x2 means xi plus 1, that is x1 plus 1. So when I take x1 plus 1, that is x2. So a xi will be now x1. So when I take it, 17 into x1 is 2, what has been taken, 17 into 2. When you take it, it is the one what we are considering it a xi, and here we are going to take it, it is plus c value. Actually the thing we get it as 77. Okay, see, mod 100 it is 77. I get the value 77 by 100 is 0.77 is a random number 2 or R2. Similarly x3, x4, x5 and all these things we are going to calculate in the same sequence. This is what we can see, show that in a linear congruential method, LCM, it is we are going to find or generate a random numbers in sequence. So what are the characteristics of a good generator? So here we are going to generate a sequence of these things. So the characteristics, there are a major characteristics, that is what is the density of the random numbers which are ranging from 0 to 1. So here the very first thing is that the values which are assumed by the random numbers, it is I is equal to 1, 2, 3 and so on. Here they leave no larger gaps in between that. That is between 0 and 1 what I am taking, the random numbers which are, we can say that they are lying between 0 and 1. Now it should not take larger gap. For example, the random number was 0.1 and the random number 2 is 0.8 something. If I get a very large gap like this, it should not leave out the gap. Here you can see in the previous number, the thing is random. In our example, the random number R1 was 0.02 and R2 was 0.77, what I could say. Like this when I take it, and R3 and so on, if you just check it out, here it will not be having a large gap here. It is very small. That's what we can say, that the density of these numbers lying will be more. Now here, if at all, if we have, okay, if the problem is that instead of a continuous, each Ri is a discrete. Here we had taken a continuous within, that is 0 to 1 what we have taken it. Instead of this, if a random number is not continuous, it is a discrete. Ri is a discrete. What should we do? The solution is that here the large integer for modulus m, we need to take the mod m to be a large, very large integer, so that the approximation will be appearing to be very, very small, or we can say that the approximation appears to be on the of little consequence, that is very small, and a little consequence what we can see it out. The maximum period, here the maximum period, what we want to do is the density what we are going to